Hello, today we talk a little bit about Matter, the new open standard for smart home. So be warned, we are going a little bit deeper into it. So it's not a video for the typical consumer only who wants to know a little bit what's Matter and what kind of component and how he can bring it together. So we're going a little bit into the specifications that you understand how Matter is really working. So first an overview, what is Matter? Like I said before, it's an open standard for smart home. Yeah, there are already a few standards out there like ZigBee, Z-Wave and Bluetooth Low Energy Mesh. Question rises up, why a new standard? Again, we will see later the advantages and that it's making really sense to having here a new standard. We will see a few advantages from Matter. The specification is quite new. It just released at September 2022 by the CSA, so the Connectivity Standard Alliance, formerly known as ZigBee Alliance. So they choose a new name because they are also involved now in the Matter Alliance, in the Matter specification. So Matter is an IPv6 based network technology. So the underlying technique there is an Ethernet, Wi-Fi and Thread. I mean, I introduced you already in Thread and also quite new technology. But actually Matter can work with every IPv6 based network technology, but there are not so many out yet, but can be later added. There is also BLE part of Matter, but BLE is only used for commissioning. So it's sometimes confusing a little bit. So it's part of Matter, but not on the main stack for the main communication. When the commissioning is done, then there is no use from BLE anymore. Matter have a focus on reliability and security, and of course interoperability. There it uses cluster library. Knowing the cluster libraries from ZigBee already. I will explain it later a little bit. So the ZigBee Alliance, now the CSA, bring from ZigBee the cluster library here inside. It's supported by a lot of companies already, like Amazon, Apple, Google, Nordic, Samsung, IKEA, LG, Schneider, Electronics and so on. And they're already, even when it's quite new, a lot of devices outside, especially like with Amazon and Apple HomePod and so on, you have already Matter included. So they have quite interest that it's working also on their products. So let's take a look on the layers. Here you're seeing the layers. We're having here network access layers, the internet layer, transport layer, and the application layer. The downer layer, are not interesting for us at the moment. The important thing is that they are based on Ethernet, Wi-Fi, and 802.15.4, the IEEE standard. And on the top there, we're having either Thread or normal IPv6. Thread with IPv6 and UDP. Can be also TCP as it's implemented. But the normal IPv6 have also TCP and UDP. And Matter is only the application layer. And this is a big difference with the other standards. So it's working with infrastructure which we have already at home, maybe a Thread network, maybe new, but Wi-Fi and Ethernet normally you have already at home. And Matter is just the application layer on top. I didn't put here Bluetooth Low Energy inside. Sometimes you see it here on the side because, it's confused a little bit. From the normal communication, BLE is not used for commissioning only. Here we're seeing a typical topology. We're having here our LAN and wireless local area network. Our DSL router can be connected also to the internet. Here we're having our thread network, and here border router which connects these two networks. And you're seeing here already a lot of devices. Yeah, when you need not a high data rate and you want to save energy, you are using normally something like thread. And like for a lamp, a switch, or a thermostat or something. And for all other products where you're needing more data rate or which are already there in your network, like your mobile phone, you can connect with Wi-Fi to your network. The border router connects them so to like the HomePod Mini or something can be then a border router. What is interesting, this is not a meta network yet, this is the infrastructure, so which is part of the meta network. It depends on. There can be the border router can be part of the meta network, but and the DSL router, but they don't have to. The lamp and the switch normally are part of the meta network. And we're seeing here what is a meta network. One meta network is identified, or it has the name fabric. So it's identified through a 64-bit fabric ID and a root certificate, root CA. So this is quite important. So you need a trusted root which have a certificate. You normally install it through commissioning or something like this, and this certificate you trust, and the nodes itself gets then a node operational certificate, a NOC short, and a 64-bit node ID. So this means when we are building up a meta network, it's identified through the fabric ID and the root CA, and a node in this network is identified through its 64-bit node ID, through its own certificate, and of course also the fabric ID it's belonged to. So that it has also the root CA, or knows from the root CA. Let's first take a look on the basic concept how Meta is working. It's using cluster for controlling and defining properties of the devices. This cluster, it adapted from ZigBee before, from the ZigBee cluster library, so it's working quite similar. And a cluster is a collection of attributes and commands which belong together, and also events. For example, the cluster on-off has the attribute on-off. It can be either true or false. And there is a client cluster and a server cluster. The server cluster holds the attribute, and the client can change the attribute or sending commands that the attributes are changing to the server. When the clients then, let's see here an example. We're having here a switch. This is a client cluster from the on-off, and we have here a lamp, which is a server cluster, so server on-off cluster. At the starting, the attribute has the value false, and the client then can send a cluster command, an EM message, which called interaction model message. We will come to the interaction model a little bit later, and we can send as a command on or toggle. They are coded. On would be 1 and toggle 2, and then we're changing the attribute on the server. We're changing this attribute from false to true. And then, as behavior, the lamp goes on. When we switch the lamp off with the client here, so we are using the switch again, then the command off or toggle is sent to the lamp again, and the lamp goes from true to false again. And there is also something which is called endpoints. So we can define endpoints where I can set multiple clusters there which are belonging together. So a lamp can have on-off cluster, for example, but could also have a level control when we can change the brightness from the lamp, for example. Or if it's a color lamp, there can be also changing the color of the light. Yeah. We can then send also commandos there. There are also events which are quite similar to attributes. The events happen normally when a condition appears, like thermostat. When the temperature is over a specific values, then the attribute, the event is then called alarm temperature is too high or something. Then the attribute alarm or something like this is set to true. This is a basic concept, and there is a cluster library also, the same like in ZigBee, where are a lot of clusters already predefined. And there are a few basic clusters for identifying, for example, the devices for device discovery and to storing information from the device. Then we having there also the endpoints, which I said before. The endpoint 0 is always reserved for the basic clusters which you have to implement, and endpoint 1 to 254, I think, or 55, you can choose for your device property which belong together. So when I have a lamp, I can make a collection to endpoint 5, for example, and put there all clusters in which belong to this device, to the lamp. And when it's on the same point, also like a thermostat, then I can place it on another endpoint, like endpoint 6 or 2 or 3, and can separate them, the logic and the data from the lamp and from the thermostat, for example. Maybe a little bit similar concept like the ports from UDP and TCP when you want to compare it. Now let's take a look on the stack, the meta stack itself. Yeah, it's also layered, and we're having here different kind of layers. On the top, we're having the application layer. This is where the business logic is implemented. For example, when I get the command to switch the attribute from the lamp, then here I program that the lamp is really going on. This means, or off. This means I can set the pin, for example, from the microcontroller to low or high. On the downer part, we have the data model. The data model describes the supported operation with the cluster libraries. So I define actually the cluster libraries which my device and node is does support. Then we're having the interaction model. There we're describing what interactions can be done with the devices. Yeah, we're having now the attributes and the command, but from the client and the server, what kind of interaction I can do. And there are 4 interactions defined: read, write, invoke, and subscribe. Yeah. Read, I can read out an attribute or an event. Yeah. Write, I can change the values there from the attribute directly. Then I have invoke. With invoke, I'm sending commands. This means, for example, toggle or make the lamp on or something like this. This would be a command. I mean, I could also make it with write and changing the attribute, but there are commands which are not changing only one attribute or which doing something. So it's better to using then commands here. Subscribe, for example, if I want to subscribe to a service, to something that I get regular data and I don't have to ask every time for the data, so I'm not polling them. I get the reports periodically, for example, or if something is changed. For example, if something is over the limit, like the temperature, yeah, we're having alarms there, then I get a message or the alarm at the door lock or something, then I can subscribe to this information. Also periodically for the temperature, for example. Then down there we're having the action framing, and this is how to serialize interactions and create a binary frame, a binary format. Yeah, is there? It's using TLV, so type length value format, for structure it, and then it will be coded that I'm getting a binary frame for the interaction which we're having here. Yeah? For the read, we're having the information, what we first the command, we have the data inside which we have to send. For example, when we write an attribute value, then the data format from the attribute and so on. And this is all coded in a TLV, type length value format, and then transferred in binary form. Then the encryption is coming. We have here the frame which we generated before will be then encrypted with a normal encryption algorithm which we know already from IEEE 802.15.4, so the AES CCM algorithm, so quite safe, so symmetric encryption. The key exchange is a little bit interesting. I mean, how it's generated, it's a little bit more complex way, but it's quite safe. So, but the encryption itself, it will happen with AES blockchain algorithm, with CCM. And at the end, there is append message integrity code. So our data is encrypted, and also the encryption is there with our message integrity code at the end. Then comes the generation of the the generic meta frame, where we are adding the routing information and the security information, that we can decrypt the message later, and then the message is directly sent when we're having TCP. When we are not having TCP, then we need for a lot of operations a reliable protocol, and UDP is not reliable. We don't know if the message arrives the receiver or not. So for this, Meta implements also a message reliability protocol, which guarantees that the UDP package later arrives, so we're getting acknowledged back from this. And we're having there the BTP, the Bluetooth transport protocol. But this is only used with the commissioning process, and uses then Bluetooth and not the normal TCP UDP connection. One of the biggest problems in smart home standards is actually how do I bring my smart home product, like a lamp and so on, my new product, into my existing network. This is not so easy actually, because like a lamp or switch, they don't have a touchscreen or any possibility for putting an input inside or something, so I cannot set a password there. So it's a little bit difficult. You can make it on a not reliable, on safe way, like you're pushing two buttons at the same time and so on. There was a solution like this before. Or you have a short moment where the connection is not encrypted or so on. But they are all not so safe and not satisfying. Meta goes actually a quite nice way, and I would say also it's a quite safe way. you're having a passcode and you need to exchange the passcode. So you have the passcode on one side on the product, normally like on the lamp, which you want to commissioning. And you have your commissioner. So commissioner is, let's take a look at the topology here. We're having something which is called the meta controller. This is the commissioner which brings the new devices over Bluetooth Low Energy in our meta network. So the new device which we want to bring in has no ideas about the credential and the connection, the credential to the thread network, to the Wi-Fi network and so on. And now we have to exchange them on the safe way. And one way is the new lamp here, which we want to bring inside, has a passcode stored. And we have to bring the passcode to the controller. And this we are doing through exchange. Either, let's say my controller is my mobile phone, I can put the passcode there inside, and it can stand on the lamp, for example, with the label or with the QR code. I can also scan it, and then the controller has this passcode also. It doesn't have to be a complex passcode. This is just for the first connection. And the passcode itself will not be an exchange. There is a mechanism which create a key out of this, which is more safe. So after the preparation, we're making the device discovery, searching for the devices where we're having the passcode via BLE or DNS search discovery. Normally over BLE when the device was never in the network yet. When the device is already connected to the thread network, for example, then we would use DNS SD. But let's assume we are using now Bluetooth Low Energy for this. Now when we found our device, we are using a procedure which is called PACE. It's short for Passcode Authenticated Session Establishment. Doesn't mean something different than just generating from the passcode a common key for the communication between the commissionee and the commissioner. The commissionee is the one which we want to commission, and the commissioner is the commissioner. And we generate a common key without sending the passcode. This procedure is called PACE. So we are sending always part of the encryption, the other we exchange them, but not directly as the passcode. And after we establish such session with this code, which is with this common key, so we can have a symmetric encryption again. And then after this we share the credential. The credential means the commissioner installs a NOC, so the Node Operational Certificate on the commissionee, like on the lamp, and also give it a node ID. And this is for Meta part. And when we're having the Wi-Fi or thread, then we also as a commissioner sending also the credential for the Wi-Fi network or the thread network. After this, the commissioner says now, you have to join to the network, and the commissionee try to join the network with the credential. Then there will be a new device discovery with DNS SD. That the commissioner gets the IP address and so on from the commissionee. Then they're generating a session key with the procedure case, it's called. This is the certificate authenticated session establishment. This will be used then every time when there is a session going on between two Meta devices. So it's actually quite safe. This means we're having a key, always a new key, when there is a new session between two devices. So from end to end, we're having there an encryption. and also we generate it here. So from the certificates which we are having, the knock from the commission here and the knock from the commissioner, then we are exchanging the certificates, which sending always the public key from the devices inside. So this means the commissioner has the public key from the commissioner, and the commissioner gets the public key from the commissionee. And they have also a private key, and then they can exchange data. And this is then used for your information exchange. And after this, we're having a finalized, so a clean up. For example, we're having here before, I didn't put it inside, something like a fail-safe, and the whole procedure doesn't work. We have first to store the credential before, and also variables and so on in a fail-safe state. And when the commissioning is not successful, then it would go in the fail-safe state. And if not, it can delete all the parameters. This is a clean-up procedure. So we're seeing our security is already quite good in Matter. After this, everyone has the certificates. It's the same system like in SSL, for example, like we know it in the internet, using certificates and generating from this a session key, so no one can listening what we are talking through to Meta devices. Yeah, also not the other devices when they are not involved in this session. And again, we are using here the symmetric encryption AES, CCM, and it's quite safe. And on the Ethernet, it's separated. So on the downer part, we have normally already security Ethernet. This normal person don't have access to it, so it's separated the hardware. And on the wireless network like Wi-Fi, we have another encryption, so the basic encryption on the network layer. And this is also true, of course, for thread. We're having already the network encryptions there, so it's even double encrypted if you see it like this. The next feature which Meta have is multiple fabrics. So this is important for the interoperability. A LAMP, for example, can belongs to two fabrics. This means it has then also two node IDs and two node operational certificates, and can be controlled from two different networks, Meta networks. This is important when you're having different kind of ecosystem from different companies, for example. They are slightly different and it's not the same fabric. You can still bring your LAMP in both of this fabric, and the switch, for example, from one fabric can then change the state of the LAMP, and also from another branch the switch can also change the state of the LAMP. Yeah. The next thing is to the interoperability with already existent smart home devices, especially ZigBee and Z-Wave and so on. And also in Meta there is something, a mechanism which supports this, which is called Meta Bridge. Yeah, for ZigBee is actually quite easy, but you still need another hardware. So you're making a virtual device here, a Meta Bridge, which having different endpoints, and all endpoints represent one node in the ZigBee network, so that you can control with a Meta switch also a ZigBee node, like a LAMP, a ZigBee LAMP and so on. Yeah, also possible with other standards like Z-Wave and Bluetooth low energy mesh and so on, if there's something out. Question is, of course, there is support. If the brands also bring devices like this, and you still have to buy them, so a Meta Bridge. Maybe at the beginning, it will happen later, not, I cannot say, but it's defined in the meta specification. One other important thing which is in meta is the over-the-air update. So you can have a OTA provider and an OTA requester. It's also handled over cluster. Yeah? So you're having there the provider implements the software update provider server cluster, and the client the update software update provider client cluster. And there is a protocol which is called BDX, where then the firmware is transferred. Normally, such a provider is a more complex device, like Apple HomePod, for example, and it gets the new updates then over a database or over the internet. And when it have a new update, then it deliver it to the OTA requester. Yeah, and the requester, the normal process is that it's having a flash, an external flash, where it stores then the new firmware. And when the transfer is finished, then you have to confirm it on one way. When there is a button or something, you confirm it with a button, for example. And if not, then the OTE provider, you can also confirm it over the OTE provider. And then normally the device starts itself new, so a reboot, and it starts into the bootloader and then making a firmware update and taking the firmware from the external flash and program it in the microcontroller or system on a chip. This was now a little bit deeper introduction how Meta is working. Of course, it's still don't go so deep into detail. I mean, I read a lot from the Meta specification. It's I don't know how. There are 700-800 pages or something, and then you're having the cluster library, having also a lot of pages again, and so on. So if you want really to go into deeper, you have to read a lot if you're a developer. But to understand the basic concept is for this already important. And yeah, still a question arises: will Meta be the new smart home standard? Will it rule all other standards? And if you ask me, yeah, I believe so. First, it's just on the application layer. This is a big advantage. Yeah? Before, ZigBee, for example, have its own framework, also the downer layer defined and so on. But it's then only on the on the ZigBee network, so we are not having Wi-Fi also included and so on. And now we're having an IPv6 network, and it can be even expand through the internet. Yeah, so it's not bounded through any location. Important thing, it has to be an IPv6 network. This means we're having high data rate and low data rate possibilities with low energy consumption, and we're having there all advantages. Thread, I made already videos, also a new standard, and I see there also a lot of potential, and it's also quite great. Another advantage is, of course, that everyone from the big companies, it's already included there. They have even already products out like HomePod and from Apple and Alexa and Siri, Google, and so on. They are already working with this, and they are working also together on this. And it's an open standard, so this means you can download the specification, not like with Z-Wave, for example. Only when you are a member you get it. With ZigBee you could also download it, but even with Meta there's even a stack available, so a GitHub where you can download a free implementation of Meta. And the same is with Thread and OpenThread. Yeah? Google provides their Google Nest an open thread which you can download and which you can adapt for your hardware, and a lot of companies does it already. So, and also, of course, the security. ZigBee with the former how to say, profiles like home automation, ZigBee Lightlink. There were a few things like Lightlink, which have a secret key for all who signed a contract and so on. It was not the best solution for anything, and these mistakes they didn't do in Meta. So it's all open standard. You get the software, hardware, and can develop it, like Nordic have already implemented it in a NRF Connect SDK and so on. But you're still a little bit complex. You have to find a little bit how it's working and so on. It's of course not so easy. But yeah, it's doable, and I like it, especially the interchangeable, the interoperability and so on from the devices, and that they are all working together. Yes, this was it for this time. Hope it was understandable. Don't forget to put a like on it if so, and see you in the next video.